The atom is a basic unit that we are all familiar with. It contains protons, neutrons, and electrons. Given the periodic table, we can identify the atomic number. This recognizes the number of protons and electrons in a neutral atom. What the periodic table doesn't show us is that each element comes in many different isotopes. This means there are varying numbers of neutrons. For example, lithium has two isotopes, lithium-6, which contains 3 protons and 3 neutrons, and lithium-7, which also contains 3 protons but has 4 neutrons. As you can see, not every atom has the same number of protons and neutrons in its nucleus. As you move down a family, the difference between the number of protons and neutrons increases. This difference causes energy to be released in the form of radiation.
So how does radiation work? Well, to understand radiation, you have to understand the fundamental forces that we have. And so if this up here is a nucleus, so the red ones are going to be the protons and blue ones are going to be the neutrons. What we find is if we look low on the periodic table, so this is neon, neon's going to have 10 protons and 10 neutrons. But as we move up the periodic table, so here we got the same number of protons and the same number of neutrons for calcium. When we move up to tin, you'll find that the number of protons is going to decrease compared to the number of neutrons that we have. And if we get up to uranium, we have 92 protons but 146 neutrons. Well, why is that? Well, the reason why is that the nucleus is held together using something called the strong nuclear force. And so all these nucleons are held together by this force which holds the nucleus together. Now the nucleus would love to shoot apart, and the reason it would love to shoot apart is you have all these positive charges up here, all these positive protons, and when you have a small enough atom, the strong nuclear force is able to hold it together. But when you get something like uranium, it's got 92 protons in the center, and so you have to have tons of neutrons to hold it together. And even with those tons of neutrons that you have, sometimes it has a tendency to fall apart. And so this chart takes a second to get your head around it, but essentially what we have on the bottom is the number of protons, and then on the side we have the number of neutrons. And so you would think if the number of protons and neutrons are always equal, then we have this perfect line that goes up here. But as I showed you on the last slide, we tend to get more neutrons the farther we go up. And so you can see that this graph tends to drift towards the neutrons. So as you get way up here with like 82 protons, the perfect number of neutrons to have would be 126. And so what you find is that if an atom exists on either side of this perfect line right here, it's going to give off protons, neutrons, so sometimes they're going to change just to get back to that equal point, or that perfect ratio of neutrons to protons.
The 3 types of radiation that we'll be looking at are alpha decay, beta decay, and gamma decay. Alpha decay releases a particle with 2 protons and a mass number of 4. In essence, it releases a helium particle. However, alpha decay is the weakest form of radiation and cannot even penetrate a piece of paper. Beta decay releases an electron or a positron. It is a little stronger than alpha decay, but is stopped by a piece of aluminum foil. Lastly is gamma decay. It does not release a specific particle, but rather the movement of protons and neutrons within the nucleus releases energy in the form of gamma rays. Canada is a leading nation in nuclear energy and supplies almost half of the world with radioisotopes. We supply about 80% of the world's cobalt-60 from the CANDU reactors at Chalk River. Let's look at how radioisotopes are used in Canada. Let's begin with nuclear imaging. X-rays are a well-known form of nuclear imaging. They're commonly used to form images of broken bones, teeth, mammograms, and bone density scans. X-ray machines pass small dosages of radiation through a patient's body, and the result is a black and white image of the selected area. CAT scans are a more complicated form of nuclear imaging. CAT scanners take many photographs of the same image and then create a 3D photograph of the desired area. The scan looks like slices of the human body. The only way to obtain results identical to those of a CAT scan would be to perform surgery. This makes CAT scans a very useful tool. MRIs appear to be the same as CAT scans, however, the technology used is very different. When performing an MRI, radionuclides are inserted into a potentially problematic area. After injection, the radionuclides will emit radiation. This radiation will be recorded and observed to formulate an idea of how the organ functions, versus a CAT scan, which observes structures within the body. Iodine-131 is a radioactive isotope that is used in nuclear imaging to locate brain tumors as well as measure cardiac output and determine thyroid and liver activity. Carbon-14 is another radioisotope which is used to study metabolic processes. There are two branches of radiation therapy, brachytherapy and teletherapy. Brachytherapy is used to treat patients with Hodgkin's disease as well as larynx, cervix, and skin cancer. For these types of cancer, direct radiation or the injection of radiation into a tumor is the best option. Teletherapy is radiation that is directed at the body from a distance. This is the most common type of radiation, but because it is directed at a patient from a distance, the side effects of radiation are more widespread.
The radiation from the cobalt-60 destroys the cellular machinery in the cancer, thus killing it. You can see the patient getting irradiated with the cobalt as we speak.
Smoke detectors use a small piece of radioactive metal called americium-241 sandwiched between other non-radioactive metal. This sandwich inside the smoke detector senses the conduction of energy and current through the area. When smoke enters the chamber in front of the sandwich, it interferes with the current and triggers the alarm. The radiation emitted from a smoke detector is less than the natural radiation emitted on a daily basis and is therefore not very harmful.
Bend it a bit.
Is a non-chemical process that eliminates harmful bacteria in the foods we eat. Studies on food irradiation since the late 1940s have proven that irradiation does not change the taste or nutritional value of our food. Irradiation of food does not cause the products to become radioactive. In fact, food irradiation is very beneficial because it prolongs the shelf life of foods and allows us to get our money's worth. Although radioisotopes and nuclear energy have many beneficial purposes, we cannot ignore the consequences of this technology. In 1945, Japan fell victim to a merciless attempt to end the war by using the first atomic bomb. The event remains prominent in the history of both Japan and the United States as it left millions devastated for generations. Unfortunately, Japan has experienced yet another nuclear tragedy. In March of this year, the reactors at a nuclear plant in Fukushima exploded violently, sending radiation into nearby neighborhoods and citizens into the shelters of gymnasiums. The effects of these events will last for generations. The following are radioisotopes that perform specific functions in today's world. Because Canada provides nearly half the world's nuclear energy, we rely heavily on radiation technology. In the medical world, it is used for imaging and diagnosis as well as treatment. In the non-medical world, it's used for agriculture and industrial use. Lastly, nuclear energy is very important to the Canadian economy as well as the global economy. As you can see, radiation technology plays an important and beneficial role in your everyday life.